here. Ian got his undergraduate in metallurgy department and then went on to School of Mines and got his PhD. And he's not the only Doc Harvey in his family. His father, Malcolm, got a PhD at the University of Utah back when they had a ceramic engineering program. It's now part of material science. And he went to work for Rocky Flats in Colorado and worked in the nuclear industry for a while. And then he decided that he was done with that and came to Utah and taught AP students. And he ended up teaching my daughter at Bountiful High School, and she loved Doc Harvey. She couldn't get enough of him. And he must have taught her well, because she ended up getting an NSF fellowship to do her graduate school. So we have a great connection with the Harvey family. Ian, when he got his PhD, went to the Bay Area and worked in the semiconductor industry. Came back and worked up in Logan, I believe, with Bournes. And then he came to U. And he taught at the U and did a lot of work in the NanoFab lab, working with students doing MEMS, so making small micromechanical devices back when MEMS was new. And a very talented person, so talented that Princeton wanted him to come, and he spent 3 years at Princeton. He's got the same problem I had as a kid, and that is his dad wanted him to work. And his dad owns this huge ranch up in Wyoming, I mean huge. And so his dad lassoed him and got him to come back to be around. And so he's kind of done some different things, worked in the medical industry and also worked at an innovation center up at Weber State. And one of the things that I hope you find out from this lecture today is you can do things which are very different than what you've done before. So when I invited Ian to come, I thought he was going to talk about nanomaterials, or at least small devices. And I was surprised that he was going to talk about fiber composites. And so that is a real talent. If you can go into a new area, you can contribute, and that's what Ian's done his whole life. He reminded me, and by the title of his talk, about someone else who is also very creative. He reminded me of some work my father had done, and so I'll just tell you real briefly about that. His title of his talk was something like Puffs of Right to Flights of Fancy. But the reason he talked about that is because they made whiskers out of what are called rice hulls. So my father was consulting for one of the Corning companies in California, and they had a huge pile of, you might call it rice dust or rice husks. They called it rice hulls, and they wanted to take and make silica out of it. Of course, there's a lot of silica in that, but he said, no, don't do that. He said, there's an intimate mixture of carbon and silica, and you can make silicon carbide, and it'll be much more valuable. And they said, no, we're interested in silica. He said, well, do you mind if I work on it then? They said no. And so he, at the University of Utah with some students, showed that you could make a basically carbothermal reduction of silicon carbide, or silica, to make silicon carbide out of a waste material, back before recycling was really cool. And because you can use carbon monoxide and SiO as a gas phase, you can transport as gas. So if you have a little bit of iron around, you've got a great way for a VLS surface, and you can start growing whiskers. And they did. Wayne Brown, who was dean of the college, said, oh, I want to do this. He was very entrepreneurial. And so he bought the patent, and he started making silicon carbide whiskers back when Research Park was just kind of in its beginning days. And with that, they sold that, and it ended up with a company in Pennsylvania who ended up, their company was called Greenleaf, and they've put it into aluminum oxide as a substrate, making cutting tools. And then one of their salespeople tried to figure out what it was good for. and he found out that it was excellent for superalloys. So they ended up doing high-speed machining of superalloys with a product called WG300. You got to have a code name for things to market it. And they made a boatload of money. So whiskers are just single crystals of what you're going to hear today. What I want you to realize is you can look at things and you can figure out different ways to do things. That's what Dr. Harvey's done his whole life. And we're delighted to have him here. Let's give him a big round of applause.
I appreciate the attendance here. I'm flattered because I understood there were like 5 students in the class, and so thanks for bringing your friends and what. Yeah. Thank you, Raymond, for that very nice introduction. I'm going to just talk about some things that, how I spent my summer vacation last year at Weber with a bunch of very enthusiastic students who wanted to help us figure out how to develop new rocket nozzle materials and also to develop a realistic test for those materials using a hybrid rocket motor. And so there's a couple of different aspects of this. Dustin Birch and Spence Peterson are both graduates from the University of Utah Mechanical Engineering program. And Spence is now teaching part-time and also working at Northrop Grumman. And so he's got a nice gig going. And then Professor Birch assembled this group of students together who love to build rockets. It's like making light and smoke and noise and having a lot of fun. My involvement was mostly in designing and building the rocket nozzles themselves, the materials, and making and figuring out how to test these things. So that's what we're going to be talking about. This is a rocket nozzle, and I should have pulled one out of my backpack. Yeah. So I'm going to pass this around. This is a 3D printed rocket nozzle made out of high temperature thermoplastic. So what we wanted to do was develop a technique that would allow us to use additive manufacturing to create a preform that was near net shape, and then very rapidly sinter this into a dense compact. And I'm going to explain why that objective is important. So we were trying to qualify new materials, and then the long-term objective was to actually create a graduate certificate in high-temperature composite materials that would be jointly taught between Weber State University and Utah State University. So let's look at the rocket nozzle. This does not have the exit cone on it, but it has the combustion chamber and its associated cone here leading down into a throat with a very small orifice, and then the exit cone would be coming out of here. And so the idea would be, where do you need high dimensional stability during the course of the launch? And that is right at that orifice right there. It can't stand from a design standpoint, from a performance standpoint, it can't stand to abrade or ablate or change in its dimensions so that the rocket performance itself would change in performance. And so this carbon-carbon, which represents carbon fibers in a dense graphitic matrix, is one of the materials of choice because of its manufacturability and because of its performance. So what we're looking at here is the section of the carbon fibers, and then the representation of the matrix there. So Raymond Oh, there's one other comment. There's a really important piece of the puzzle that he missed when he was talking about his father with the rice hull project. Well, his father was my dad's thesis advisor. So you kind of missed that. That was an important connection point. But I wanted to also just comment on something else that Raymond said, and that is that when you folks go out to your first jobs, I'd like you to have the confidence that your eyes, being fresh eyes, having never seen kind of the way we've always done things, you've got to have the confidence that you are very valuable just because you haven't been invested in the way things have always been done. Does that make sense? So I'm going to just share a little example here, and it's going to go to this point right here. So I'm hearing this thing about carbon and rocket nozzles, and it's all kind of almost making sense. But until I actually go to the factory where they make these things, and I see this 40-year-old knitting machine that's winding carbon fibers in the circumferential direction, and it's winding fibers in the radial direction of this billet. And you can kind of see that. I'm sorry, this is the only one I could find on the internet, and it was really old because the technology is really, really old. So it's not very clear. But you're watching this winding, and then the very last step is the axial winds. And that happens. So imagine this thing. This is like almost 3 feet in diameter, and it's 4 feet tall. So it's a big billet of woven carbon fiber. And the very last step involves these very long, these 4-foot long needles that are going up through here and then stitching the carbon fiber and then bringing it back. And so sitting right here, not shown in the image, is the old graybeard with his little half-moon spectacles and a pair of tweezers doing this. And you're watching him and you go, I better not bother this guy because he's doing some really fine, detailed work. And so it turns out that his knitting machine was made by a company called Aerospatiale. You may have heard of it, a French company, 40 some odd years ago. And those guys somehow figured out how to translate the technical language from the French, and they figured out how to, build these billets. Okay, well, that's carbon fiber. How do you get a dense graphitic matrix into those interstitial spaces? So here's in the factory, and you've got this billet now, and they show you how they take the billet, and you walk over into this other part of this huge high bay, and there's this massive, massive vat of stuff that looks like it came out of double toil and trouble. Fire burn and cauldron bubble. This is really some nasty looking stuff, nasty smelling stuff, black tar pitch. And they put this billet in the pitch, close the lid, pressurize it so it's hot under pressure, and the whole idea is to infiltrate the open spaces with pitch. Okay, this might be a thermoplastic. In this case, it was a coal pitch. But if you then take this thing out of the batch, you have to cure it now, and so there's a carbonization process which drives off some of the volatiles, and so it's just a heating process. It may be under vacuum, and then it goes into a graphitization process where think about this. You need to create ingress cracks in the stuff you just polymerized so that you can go through the process again and have an ingress path for the next step, because you don't just do this once. If you do it the first time, when your target density is about 2 grams per cc is the ultimate density that you want to achieve, The first time you might only get 1.5 if you go through that cycle of infusion, carbonization, graphitization. So those are 3 separate vats, the last of which is this big giant vacuum chamber heater. And so one trip through, you get like 1.5 grams per cc, and then you pull it out and you look at it, and you kind of this artisan, is the pizza done yet? And you go, no. So you go through the process again, and each time, you know, it's like every step of the process takes like 3 weeks, and every step of the process it takes this person who's been around for a long time to say, is it done yet? And so when it gets to 1.8 grams per cc, and that last little bit was really hard to come by, you're looking at 12 months for that billet to have gone through the process from weaving to, and so you go, no wonder we are behind in the hypersonic race, because we know how to build these missiles, but we can only build like a couple of them per month, and the manufacturers are going, we need to be able to build like 100 of them per month. And so you look at it and you say, that's a problem. And so here you are, the person with brand new eyes who maybe came out of a different discipline, and you go, why on earth are you doing it this way? Why on earth are you relying on diffusion physics when it's inherently going to take time? And what can you do? I'm asking you, what can you do to modify the diffusion coefficient in this case? What kinds of things would you do? Any ideas? Please.
Is this an oven cure or an autoclave?
It's like an autoclave, but a heated autoclave. Are you talking about the infusion or the subsequent steps? They're heated. Some of them are under pressure. The infusion is under pressure. The carbonization is under vacuum. Heated. So you're trying to get this resin into the system. You're trying to get the volatiles out of the system. Let's just talk about the resin going in. What kinds of things would you do? Audrey, right?
Yeah, can
Okay.
you modify the porosity at all, so that way you get more to come in? So.
That's right. That's one of the big things that they do is they say, well, I don't want too high of a carbon density, because if it cross-links too much, then it's hard in the graphitization cycle to crack it again and create those ingress paths. So it's not necessarily porosity thereafter, it's pathways. Yeah, so that's good. That's one way. Any other ideas? You're going to play with viscosity, you're going to play with surface tension, and then the obvious things are temperature and pressure, right? So this is what they're doing, and so there's a lot of work going on at like Oak Ridge National Lab on how do you develop a new polymer with an optimum viscosity and surface energy that would help it penetrate, maybe by capillary action or some other thing. Well, the problem is you're still dealing with the same old physics. It's still, you maybe knock off a month or 2 months by doing something like that, but you're not getting to the point of dramatically changing the manufacturing cycle where a year goes down to a couple of days, okay? Because you're not changing the way you're dealing with the physics. So, does everybody know who James Carville is? He was a political advisor to not Jimmy Carter. That was a long time ago. The other guy, Bill Clinton. When he said, "It's the economy, stupid," and then that helped Bill Clinton get elected that cycle. But here I'm just saying we've got to think about the physics here, and so this artisan technique that produces a lot of scrap, a lot of waste, besides taking a lot of time and being hugely expensive, we gotta get out of that cycle. So what I want to talk about today is a technique that's been around for a long time called spark plasma sintering. It's also been called electric field assisted sintering. The idea behind it is that you have under pressure and with a die set that is forcing the DC current through the sample under pressure and direct heating, then you can rapidly sinter the part. Okay, so you're probably familiar with hot isostatic pressing. So this is similar, except that you're directly heating the sample with I squared R heating. So you dump a whole bunch of current through the sample, it self-heats, and you get uniform heating, you get rapid heating and cooling, and when you're done, you've got a very, very nice compact, high density. So, what about this technique? So what we wanted to do was we wanted to use additive manufacturing, use high temperature thermoplastics, and build the fibers and the resin in such a way that we could do an in situ conversion into carbon-carbon. So here's kind of what you're looking at with this direct current sintering. Very low voltage, but extremely high currents and high current densities, and a lot of pressure. The system that is up at Idaho National Lab is an 800-ton system with a couple 100,000 amps. So that's a pretty beastly system. So get it up above 2,000 C, form graphite, and then you're pretty happy. What about the physics? Instead of diffusion physics, now what we're going to talk about is this electromigration. Is this a word that you guys have heard before? Anybody not heard of electromigration before? Okay. I first encountered electromigration when I was in the semiconductor world. I worked for this company here, and I did a lot of analysis on the chips, and we were very concerned about the effects of high current densities over a long time and how that would impact the reliability of the metal traces that connect the different nodes on the circuit. And so if you imagine one of these lines right here, there's a couple of different forces at play. There's an electrostatic force at play that pushes one way, and then there's the electron velocity, which involves a momentum exchange of electrons impacting atoms. Okay? So that's a force in the other direction, and this is the force of electromigration, which we call the electron wind. So imagine now, here's one of the chips that I looked at years and years ago. This is one of those metal lines. This is a cross-section. Now, the picture I showed just a minute ago was from the top view. Now I've used a focused ion beam to cross-section through a metal line. There's a metal line, there's a metal line, and then there was a vertical interconnect, what we call a via, between those two. And the test structure had been dumping current through this metal line for a long period of time. And so what you get is you get the momentum exchange that pushes atoms from one side of the metal line over to the other side. So here's the equivalent. So you get something that was thin. This is the original thickness of the metal line right here. Now you've got voiding, and then all those atoms pile up where they can't go any further. And in this case, they piled up to the point where it actually fractured the surface of the chip. All right, here's a little better image of the vertical interconnect, the voiding here, piling up, fracturing. So that was pretty cool. I'd never heard of electromigration, but that was pretty cool. So unlike diffusion physics, this is based on an Arrhenius rate equation and the forces that are involved with that. So there's a different kind of physics, and that physics works a lot faster than diffusion physics, okay? So we're going to come back to that. But I want to just do a little aside and talk about the role of kind of the material science way of thinking as it relates to kind of addressing these problems. I'm sure you've seen this before, the material scientists in the crowd. The idea that materials, when we think about materials, we have to think concurrently about structure, properties, processing in order to achieve performance in the ultimate product. And then this thing in the middle that means all the fun tools, the analytical imaging tools, the electron microscopes, and everything else that make our work so much fun. So I like to explain to people that material science is a foundational discipline, and that folks are going to go off in electrical engineering and mechanical engineering and make some things, but without the material science element, it's really hard. So we are applying the material science approach to this problem and saying, okay, here's our rocket nozzle, and I've got the converging and diverging sections of the nozzle, and I've got the throat. And I know that the throat has specific needs from a performance standpoint. We talked about that a little bit, the idea of maintaining dimensional stability. In the converging section, where we're having the combustion taking place, one of the big problems is you also want to get rid of heat. And you want heat to go that way, out the nozzle, and not this way out to the casing. And so there's thermal insulation questions, and then there's what is referred to as ablation, intentional design that allows materials here to undergo endothermic transitions to pull heat out, and then allow that material to exhaust out the backside. And so you're pulling in heat and you're exhausting heat. So that's one of the things that you want here. On the exit cone side, you need not only the heat resistance, but that's where you need the structural attributes, the strength, the fatigue resistance, vibration resistance. This exit cone is where all of the forces of the thrust are transferred back to the rocket. Okay, so that's where most of your mechanical properties are really important. So if we're saying, hey, I want to use additive manufacturing to print a monolithic structure, monolithic with the exception of this has got to be built separately because it's got to be converted, to carbon-carbon or some other material that's going to make it very resistant to ablation. But everything else can be printed monolithically in a common structure, printed around that throat structure. So that's the idea. And we come back to this and we say, okay, from a material standpoint, I'm talking about properties and structure. This line of thinking is all driven by the problem statement of that monolithic structure that we're trying to build. So what kind of processing techniques are we going to use? Again, just emphasizing the physics that's going to be involved, right? And between these two things, these dictate what kind of processing tools we're going to be wanting to use. And then you go in and you sift between the different manufacturers the processing tools to decide which one you want. And then, of course, the performance testing. In our case, a lot of pre and post characterization with densities and fundamental properties, but also a lot of imaging and looking at porosity and things like that. So when I looked at that problem, I said, okay, here's a nice way to meet the additive manufacturing part of this whole thing. If I start with a throat that I've densified and I grab onto that with a robot that has 5 axes of motion, and I stick another robot on there that allows me to print carbon fiber with these high temperature thermoplastics. thermoplastics are so much nicer to work with than thermosets. And so there's really a lot of incentive to, to find better thermoplastics that can work here. So carbon fiber, very nice for the tensile stresses. Boron fiber, very nice for the compressive stresses. And so you want to mix and match according to the models of where are you, what stresses are you experiencing and where are you experiencing those. Printable rubber. Rubber is a material that's used currently as the ablative inside the combustion chamber. So it's thermally insulative and it blows out the backside, carries heat with it. And then automatic tape layup. This is a method of laying down acres and acres of carbon fiber with the plastic. So if you're just trying to build up bulk, this is a good way to do it. So here's a robot or system that the designers have figured out how to get these 5 robots to dance together and not step on each other's toes. So that's one aspect of it. Another aspect is what is the material you're going to use for the resin. So here's a phenolic. You folks familiar with TGA, thermogravimetric analysis? You heat this stuff up in a inert atmosphere, and you see how it degrades. And you can look at the gaseous effluent that's coming off of the sample and look at the composition of that. But typically, the main thing is that you look at how much of the original mass is left when you get done cooking it up to a certain temperature. Where does it start losing its mass? So phenolics. Polyether ketone ketone, ether ketone ketone, and this stuff is pretty darn good and starts to degrade about 550. So it's an expensive thermoplastic, but it works pretty well. PEEK, very similar. Polyether ether ketone, and again, it has a degradation 500, 600. That competes very well with the thermosets. One of the side aspects that we were interested in is how do you help the Utah coal communities that have been decimated by the fact that we're not burning as much coal now. We're not throwing carbon ore into furnaces, and how do we take carbon ore and make useful technological things out of that ore? How do you treat it as an ore and not as a fuel? And Professor Eddings here at the U did some work for these folks on their SBIR, and he looked at the composition of this coal pitch. Actually, go back to the first vat that I was telling you about, double toil and trouble. That's what was in it. And he looked at what the structure was. He looked at how the properties compared depending on how you process the pitch. So take the coal, anaerobically decompose the coal at different and then condense it at different temperatures. So these are the temperatures at which the volatiles were condensed after pyrolyzing the coal. Okay, so he looked at that. The folks, the customer looked at it and said, well, that's kind of the one right there that most closely matches what we're already using. The question is, Audrey, to your comment, whether or not the optimum for creating cracks in the infusion process is also the optimum when you want to have as much carbon as possible in the as printed preform, so that you don't have to infuse. What you're trying to do is prevent stuff from escaping and fuse as much as you can that's already there. So there was a collaboration that looked at the coal, and then we went and we printed some samples. So this is this is like the nozzle that I passed around, except that this one, unlike the one that you have, this one has carbon fibers printed with this PEKK out to this level, and then afterwards it's only PEKK because the carbon fibers are expensive and you don't really need the fibers out here. Okay, so there's a close-up. These were all 3D printed, and then we did some manual layup with just a carbon cloth and coal pitch, except that I couldn't resist the opportunity to play with it, and I'll talk about that in just a second. So then you go through this effort of, okay, you characterize it, how much porosity do you have? You use nice microscopes like what we have here at the U, and you build these things up. So this is how we built the pellet that was going to be formed into a throat after we got it densified. And I happened to have some boron coated tungsten wire. So I had these boron filaments, and I thought, I'm just going to throw some of those things in there and see what happens. And I had some glass cloth, fiberglass, and I threw some of that in there too. So basically it's pitch with carbon fibers and glass fibers, and there's a few boron coated wires, and then again just the duplicate of what's up here. So we took that stack and we ran this direct current sintering process on it, and that's where I had my fun. Okay, now you guys that are doing machine learning, right? There's a huge opportunity for machine learning to be applied to this process because there are so many different aspects to the processing conditions. But when you get to the point where you want to make something other than a very simple little puck that can be machined into a rocket nozzle throat, then you have to worry about what properties do you want to have again in which part of the part, right? And so you start worrying about how do I optimize the current density profile according to the profile of the complex part. It's not just maybe not going to be a disk. And so there's a lot of aspects to things like machine learning, even in this. This is just, Oh, and by the way, this is happening in a vacuum. This direct current sintering process is happening in a vacuum. And so all those little nasty volatile components, the naphthalenes and the anthracenes and other stuff, you have to kind of watch that so you don't totally screw up your vacuum system, and you also need to be aware of what you're exhausting into the environment. Okay, so here's the part as built, as pressed, and then here's the part front and back after we did the densification. And you'll note that I didn't quite get to the 1.8 that was the target. That's like, this was the first experiment. Second experiment, I'm going to show you what we wanted to do. So these lines right here are the boron fibers that I just laid down manually so that I could kind of know what the directionality was when I wanted to do my cross sections and see where things were. And I can't find those when I look at this. It's like, what happened to them? So you go and you stick it in the FTIR and you look at it and you say, okay, here's the FTIR fingerprint, the red, when we just printed it, and we have just, the coal pitch is only seen like 70 degrees C. And FTIR turns out to be a really powerful technique when you have a lot of side chains and functional groups, because FTIR, the IR modes are really good for distinguishing asymmetry. And so you get really nice fingerprints of molecules when you have asymmetry. And so what this showed us was that as we went up to 700 and 1950 and 2000, we completely lost these fingerprints because we lost all of our side chains. We lost all of our functional groups. All you've got now is carbon bonding with carbon, and that's a terrible mode for FTIR fingerprinting. It's a really good mode for Raman fingerprinting, because Raman loves the symmetry of bonds, and this is where you can pull these things out. And I didn't get to do any Raman. That was next on my list. But I started to go, hey, I had these beautiful 100 micron boron fibers, and what happened to them? Oh, here's one, and wow, I should be able to see the tungsten in this image, but everything was busted up and broken and just messy. Okay, so then you come down and you see Randy Polson down in the nanofab. Everybody know Randy? Oh, you should get to know the folks in the surface lab, because they have all the toys that can help you with, that's all the white lab coat material science stuff going on up there. And so he's got this nano CT system up there, and so he took my little pellet, and you can see that the tungsten just should be, and is, glowing. You can see the tungsten, but it's not a line. It's been totally busted up by the pressure of the DCS. I did a cross section of the fibers, and looking at the fibers, you can see that there's a lot of porosity left between the fibers, and yours truly didn't do a very good job of cleaning out the polishing media either. So this is another indication that, hey, there's a lot of work that can still be done to make this a higher density compact. And so then I took a piece of that thing and I cross-sectioned it, and so there's the remnant of a boron fiber, and there's a boron fiber, and there's one down here. So what used to look like that now looks like this after polishing. And if you go to high accelerating voltage on the EDS, you can separate the silicon and the tungsten, which at low kV that you have a nice overlap, and it's really hard to, unless you do deconvolution, it's really hard to separate the two. But at high kV, you get distinct peaks, and you can separate the two. So, wow, I was seeing silicon, and there's this boron, and it's actually boron carbide now. It's been converted, and I got tungsten all over the place. I looked at another one of those fiber cross sections, and I'm like, what is that? And aside from kind of the boron carbide that you see, which was I thought that was fascinating to have converted that boron fiber to boron carbide. That was pretty cool. But what is going on there on the edge? And I get this, rich carbon, I get this boron carbide over here, and then on this edge, and again, it's a raised edge, even though I polished it, this thing is really hard right here. And I can see that the silicon has, some of it is silicon carbide, but there's a lot of silicon there that you go, what is going on, until you come over to your phase diagram and you say, what's going on in the phase diagram? And at about 1550, you got boron carbide, you got silicon carbide, and then you got liquid silicon. And so that's what we had here. And so all my glass fibers completely destroyed, melted, and that's not a huge surprise given the temperatures that we had. But it looks like also that the silicon acted like a lubricant for a lot of stuff just moving around. And it also looked like the electromigration effect just took that light boron and pushed it away from the tungsten. And so a lot of fun stuff going on right there. What do we learn? I don't know. I was thrilled with the effectiveness of densifying that pitch and demonstrating that a single-step process that takes just a couple of hours is capable of replacing a densification process that takes months and months. The puck was really thin. I'm looking at that and I'm saying, based on the physics, there must be a better way to do this because I need a reservoir of material that can be sacrificed. It can become the porous part of it where I push the atoms into the dense part. So that's what I'm going to do. Boron fibers cracked, glass fibers reduced. And by the way, that's kind of cool because the glass fibers melted and then they reduced. And what does that mean for the ablative thing that I talked about? That's a double endotherm. You can talk about two sources of pulling in heat to the material before you blast it out the nozzles. So that's a potential aspect for an ablative material. Okay, so very quickly, when do we tie it up? Till 3. Okay. So I'm going to just dash through really quickly what these folks did with their rocket project, building the rocket motor, testing it in front of a bunch of VIPs up at Hill Air Force Base, and fortunately they didn't call the security guards after us when we did that. We got some nice press. We have the additive manufacturing tools up there to make the test pieces, the reference test pieces, which are very porous, low density, and because of that, any improvements we make should be obvious because it's compared to something which is really crappy, right? So this is looking down the throat of a piece like the one that I passed around. And then this is looking down the throat after we've done the launch. And I just got to say that being a lifelong electron microscopy enthusiast and working in a clean room for most of my life, it was really hard to think about putting this sooty, dusty crap in a beautiful high vacuum, high resolution microscope. Okay, so I'll just tell you that I called a lot of people first, and then I used hairspray to stabilize the dust so that I didn't crap up the microscope. Okay, so students really loved working on this project, and I might add that this is a hybrid rocket, and so the fuel that we're using, this is actually 3D printed ABS plastic. It's the same stuff your Legos are made out of. And so this is totally inert. And I'm not saying that Legos are dangerous. I'm saying that Legos can make pretty cool hybrid rockets if you use like nitrous oxide as the oxidizer for them. So that's the hybrid rocket approach that they used. And they did a lot of modeling work, which I was impressed with. And there you go. So my job here was, again, the post-mortem analysis, taking things apart, showing them how to analyze the materials. Yeah, I wish we could have done ramen. It makes such a difference to have nice microscopes. So you have access to these same kinds of microscopes up here at the NanoFab. If you want to take glamour shots of whatever it is you're making, where everything is in focus, take a look at that rocket nozzle that I passed around, and here's an image where everything is in focus. That's kind of unusual, but if you want publication quality images, they've got this microscope up at the nanofab, and then of course there's all kinds of electron microscopes up there as well. So again, everything is in focus. This is the key ints, and that's the the scanning electron microscope. All right. The post-baccalaureate program, this is the draft proposed set of coursework that we're working with Utah State and suggesting that we develop this. It'll be some variation on this theme that gets created probably over the course of the next 2 years. All right. So Baki Yar was one of my thesis advisors at Mines. And I was impressed by that idea. So it's like you're not going to get all the answers with your experiment, but you've succeeded if you've created another set of questions that helps guide your next steps, right? So how to identify the carbon-carbon? The physics dictates that I needed a sacrificial carbon reservoir. The observation of boron and silica is suggestive of what we might do if we want to make, ceramic matrix composites using this technique or a similar modification. What else can we do? And we'll get there because, I was talking about, how does rice husks come into this whole thing? It was the question. And so this is where the flights of fancy idea came from, is the idea that what else can you do with this technique and this approach to make not just carbon-carbon, but to make silicon carbide in silicon carbide matrix or, carbon in silicon carbide matrix. So let's take a look at one approach. So here's the rice husk. The rice husk is maybe, and these are rough numbers, and it depends, but 60% cellulose, 20% of this lignin, silica. So the direct current sintering technique relies on electrical conductivity. What can we say about electrical conductivity based on these constituents? What about silica? Conductive or no conductive? Okay, thumbs down, right? So that's glass. It's not conductive. What about the cellulose? Is that going to be conductive or non-conductive? Iffy? Kind of iffy? Probably not very conductive compared to lignin, which has a lot of these aromatic structures, which when you overlay them, it's the aromatic structures that give you the conductivity in organic materials, right? So potentially rice husks could be used as a matrix material. Let's say you put carbon fibers in them, or boron fibers in them, or silicon carbide fibers in them, and then press this, and then you can get, in theory, you can produce some nice fiber in silicon carbide matrix material. Okay, so that was the flight of fancy, and I was on my way to the grocery store to get some some rice husks. Anyway. So what else? I think the important part is this extend the reservoir, right? So let's talk about how to do that. So here's the idea behind another set of experiments, and the idea was instead of a thin little puck, make it thick, and give yourself a lot of room here to push these carbon atoms into the dense part at the bottom of the structure. Experimental design. Do they teach statistical experimental design? Who has not been exposed to DOE, statistical experimental design? You have not been exposed to it? Okay, so this is the idea of, hey, I can try to understand an experiment mechanistically, and I can design an experiment mechanistically, but I'm going to end up running a lot of individual experimental data points. The statistical approach to that thing is kind of agnostic to the mechanics. It just says, how can you most efficiently design an experiment with the fewest number of experimental runs to get to an end result, and understand where your important parameters are and where are the important interactions between parameters. And so you can do this statistically, and that's what this is illustrating here. So what I wanted to do was to make, instead of that thin little puck, I wanted to make it much thicker and then put a whole bunch of pitch on top of that as a carbon reservoir, run it through the DCS tool, densify it. So most of the porosity would have occurred up here. The compression would have resulted in something where, okay, I've got porosity up here and I've got a gradient down to the dense material here. And then remove what you don't want with machining, drill a hole in it, and you've got yourself a nozzle throat, which can be built into a nozzle. And then we can go and test it and have some real fun. Okay, so that's one approach. Rice husks might be a reasonable way to get there. What about other materials that have nice intimate intermixing of carbon and silicon? Who's familiar with PDMS, polydimethylsiloxane? Anybody? Okay, what can you say about PDMS? Have you used it, mixed it?
Yeah, it's just a nice base for a lot of things that we use.
It's what?
A nice base for a lot of things.
A base?
Or just other things.
A substrate? Okay, good. And what do you notice about it when you work with it? Is it like fun to work with?
It's fine. I don't have strong opinions about it, I guess.
You have to use gloves, right? And you have to make sure that you clean everything up, because that stuff's really oily. It's silicone. This is silicone we're talking about. And oil goes everywhere. It's really a mess. But look at this chemical structure here, where we've got silicon intimately in contact with all this carbon, and once you mix the two-part stuff together, you've got this rubbery thing. And by the way, this part here is photoactive, so you can actually use photolithography techniques to pattern the stuff. So it's really it's a nice supply chain, and it's well known, easy to use. The question is, if we put it in DC, if we pattern it a certain way and put it in the DCS, are we going to get the cubic form of silicon carbide or the hexagonal form of silicon carbide? I don't know. I just got delivery of my test sample. I was like, okay, that's the end of that. Okay, so here's another way of looking at that PDMS mixture again with the TGA. When you mix them together, you've got like 40% by volume is this, or by weight, sorry, is silica. And if you look at it with the FTIR, you get these characteristic peaks of all these other side chains disappearing, and all you're left with is silica. So if we do the same thing in the presence of pressure and self-heating, are we not going to get? I think we're going to get. I can't wait to try. So Professor Zach Fong has one of these tools up in one of the old mineral processing labs. And I was talking to him earlier today, and so we're trying to figure out how to get his old system that he got at a garage sale up and running again, because it'd be really cool to study some of this stuff down here. Okay, so we're at the end, right on time. I firmly believe in this material science approach. I'm an advocate. let the problem spec drive the materials, let the physics drive the process, and then shoot, the tools kind of fall out after that. Realistic testing is important, and it's really integral to this idea of product development when you're using the material science way of thinking. And then this direct current sintering, I think, is a blast. And so much fun. It's been around for years. People have used it for years and years for sintering metals and ceramics. But now applying it to some composite systems, I think, is going to be a lot of fun. So thank you for your attention. I really appreciate it.
Let's take some questions.
Please.
So, you said these original carbon fiber pellets were 3 feet by 4 feet.
I'm sorry, can you speak a little louder? So that we can, here we go.
So, you said the billets were originally 3 feet by 4 feet, but are you able to scale up from your current process
Yeah,
to make stuff like that?
So the question was, that billet that I suggested was like 3 feet by 4 feet. That made 4 rocket nozzles, so they'd cut it into 4 discs, and then they'd machine the center throat to the specification. And your question is, can you just?
Is your process able to scale
Oh,
up?
can we scale it up? Can we scale it up? So that beast of a system up at Idaho National Lab is the first of its size, but it has that 800-ton press and 200,000 amps. So yes, that system is able to create the current densities needed to make that. Good question. Yes?
Question about the temperatures you're achieving in the rocket nozzles. So a carbon-carbon composite is going to ablate pretty quickly. So you put, like you said, a rubber silica composite as your ablation layer?
You're talking about in the combustion chamber?
Yeah, I'm trying to understand how your material is surviving and not being ablated away.
So in the combustion chamber, so how is the material, are we talking about the throat or the material inside the combustion chamber? How's it surviving and not just getting blown out the hole?
Yeah.
Are we talking about the throat or the combustion
Whichever-
chamber?
The throat is what you're making out of your 3D printed composite.
Right. So yes, if you're talking about a single-use rocket, one-way trip, then you can get the performance that you need from a dimensional stability standpoint out of a carbon-carbon. If you're going to talk about a reusable rocket, then we have to go to these more advanced fiber, ceramic materials to maintain that stability. Yes, please.
When you were doing the SEM and you just sprayed a layer of hairspray on your powder sample and that fixed it, that kept the powder completely down?
Yep.
And it didn't compromise
Nope.
anything at all?
Nope. No, I didn't see any charging effects or anything when I put the hairspray on the
This is the same
on the
thing as
si-
hair. Just kidding.
yeah.
And is that something that you could do with like any SEM machine, or are you able to do it with that one?
So that one was a field emission system, and that one I was running under high vacuum. So yeah, I didn't want to run it in low vacuum because I didn't want the viscous flow to be pushing things around. But I did run it under high vacuum, and I was really glad when I didn't destroy anything, because that's a really nasty, expensive repair to get bits and pieces up inside your column. Yes, please.
What kind of groups or like entities are currently interested in this kind of research? Is it just like NASA? Is it like SpaceX?
Well, there happens to be a group up in Promontory, Utah, that's extremely interested in all of this.
Do you know what they do?
They make rocket engines and nozzles, and they're one of the biggest producers of rocket engines and nozzles in the world.
So if someone wanted to do an internship with Northrop Grumman, how would they do that?
I'm not entirely sure because we never got to that point in this program, but if you're interested, I know a bunch of people. So I'd be happy to introduce you if that's something you're interested in. Yes? Uh-huh. Oh, did we see any change in the performance of the material because of that silicon? Didn't look. I mean, the idea here was to see if we could densify it and to see what kind of phase transformations we could create. But I wanted, once I knew what was going on there, I wanted to develop another experiment where we could actually create a ceramic matrix material that we would test in the hot test. And so, yeah, so this was just a curiosity right here. It was like, that's really interesting. I wonder how we can use that. Okay, thanks. Appreciate the questions.
What was the rubber matrix material for your rubber silicon ablative?
There's a lot of different rubbers, and they, I guess, didn't disclose to me what rubber they used. So I don't know. But there are, for example, there are 3D printable rubbers. And dispersing glass in a number of forms into 3D printable rubber is not beyond comprehension at all.
Ian, what are your thoughts about how you deal with the alignment issues if you're going to use something that's uniaxial as opposed to isostatic if you're trying to really get fibers aligned in all sorts of directions?
The beauty of the additive manufacturing technique is that you can optimize your fiber alignments according to the stresses.
When you compress it, right?
That's when you talk to these guys that are doing machine learning and, you know, so there's going to have to be a lot of back and forth between the experimentalists and the modeling folks to figure out how to do this really well when you're talking about like a nose cone or something, or a leading edge of a wing or something like that. Some you know, complicated geometry that you're going to have to deal with current density changes and where do you want the high density material versus where can you allow it to taper off to kind of the more classical properties of the thermoplastic, the virgin thermoplastic.
Any other questions? Let's give Ian another great round of applause.
Thank you for coming.
Thank you for